Hello, and welcome to the lecture on the topic of entropy. Entropy is a topic within thermodynamics. It is the quantitative explanation of the second law of thermodynamics. Entropy has a real important role to play in understanding what the second law is really trying to say. So let's define entropy, think about how it makes sense, how it's a value that we can calculate, and it establishes a rule, and we'll look at some other definitions and examples along the way. So let's define entropy. Well, entropy is a quantity of disorder. All right, so it's a way to quantify disorder. I mentioned that a few times. The big focus being here that this is a new unit. It is the amount of energy per unit of temperature that is unavailable to do useful work. All right, it's unavailable for useful work. Think of this as a free gas. Okay, you're not going to be able to have it do anything for you. The air around you, for example, if you don't funnel it somewhere, force it into a small space, heat it up, compress it, cause a chemical interaction. If you don't do something with that air, you can't do work with it. And you would have to put work into containing that gas in the first place. So that's the idea that a free gas is unavailable to do useful work. It's useless. Now the units of entropy are energy per temperature, or joules per Kelvin. The dimensions, because the joule, of course, has the units of the kilogram meter squared per second squared, it's for a joule. Well, in dimensions, then we have mass, length squared, time to the -2, because it's in the denominator. And then, since we're also dividing by temperature, we have the dimension of temperature to the -1. Right, and this letter here, this Greek letter, denotes temperature, in the same way that T denotes time in dimensional analysis. So, what's our last point to make about what entropy is? It is mostly used when the entropy of a system changes as a means of tracking the disorder of energy. So in this way, we can, for example, compare entropy to efficiency. So entropy can be compared to efficiency, right? As a proxy for it, or as another way of looking at a system and quantifying that system. It can also be shown to always go up. It will always increase. And in that way, it establishes that, in the same way that energy can't be created or destroyed, likewise, entropy can't just go down in the universe as a whole, or in a complete system. If there's a closed system and there are systems within that closed system, then as those smaller systems interact, the larger system as a whole will have an increase in entropy, a measurable increase. And that does take us directly to the general statement of the second law of thermodynamics. And that simply is that entropy always increases, right? We've seen other ways of getting at the second law, saying that no engine can be 100% efficient. You can't completely turn heat into work, right? There's something has to get lost. Well, now we're saying, okay, well, entropy is the measurement of disordered energy. So now we can quantify that it must increase, all right? This unit, right, or derived unit of disorder must always be on the rise. The total entropy of an isolated system consisting of multiple parts at different initial temperatures will approach equilibrium and thus a state of maximum entropy, right? So the final entropy, which we'll denote by the letter S, will always be greater than the initial entropy of that system, okay? The final entropy will be greater than the initial entropy of that system. What's the system? Warming water, mixing ice and water, running an engine, letting steam cool, whatever it may be. All of those systems will have an increase in entropy, right? And you might, in the case of steam cooling, well, is that a actual increase? Well, there'd be an increase in wherever that heat went. So if the steam cooled, that maybe that heat went into the wall that the steam cooled onto, and there'd be an overall increase in entropy. All right, and that's really one of the big quantitative takeaways of this lecture, is seeing when you have a 2-part or 3-part system, how some parts, right, of a multiple part system will have a decrease in entropy, but then the other parts that have an increase, their increase will always be bigger than the decrease. Thus, the net change Well, that's greater than zero because it always increases. Okay? And interesting thing about this, everything approaching a state of maximum entropy, that is no different, no more profound than just saying that everything reaches a state of equilibrium. So every system approaches equilibrium over time, including the universe as a whole. All right? So there's something called heat death, which is a theoretical final state of the universe. The universe consisting of multiple stars that interact with each other, that are part of galaxies, that and those galaxies themselves interact with other galaxies quite a bit. That system, always interacting, will gradually move towards equilibrium. Well, what would equilibrium look like if you think about it for the entire universe? Well, since every system approaches thermal equilibrium, so too should the entire universe. And at such an eventual time, which most estimates put at hundreds of billions of years or trillions of years, which is much, much longer than the current age of the universe would be in a state of maximum entropy, because saying it's in equilibrium is the same as saying it's in a state of maximum entropy, excuse me. And thus, thus any process that increases entropy would be impossible. And this should say any process. All right. So there could be no more thermodynamic processes such as the isotherms and the adiabatic processes and all the isobaric and every nuclear process that releases energy. All of that would have to be over. And that means things like stars radiating energy, that is such a big part of the known universe today, couldn't exist. So the final state of the universe must not include stars, because it has to be in equilibrium. And the equilibrium temperature of the overall universe would be very cold, because there are very hot pockets of the universe, but they're proportionally tiny compared to the empty, very cold space in between stars, galaxies, okay, let alone planets. So that's the final state of the universe, maximum entropy, equilibrium, two ways of saying the same thing. All right, but let's look at our simple equations, our way of quantifying entropy, a measurement of disorder. Okay, well, you can see the equation we have here focuses only on the change in entropy. Okay, measuring the absolute entropy of a system doesn't always make sense, because we need a reference point, like how much entropy compared to what. But a change in entropy is the logical way of looking at this unit. Okay, so S for entropy, of course, delta is just the change. Okay, T is the temperature of the system, okay, measured in Kelvin. Q is the heat flow of the system. All right, so this is a system where it is changing, because if entropy is changing, then something about the system is changing. Perhaps its temperature is changing, we'll touch on that, but more importantly, there's heat flowing in or out of the system. And Q here is defined in the way you might think. It is defined that it is positive if there's heat flowing to the system, and it's negative if heat is flowing away from the system. Okay? In, positive, out, negative, and as far as the heat flow for the system. Okay? Now, and by the way, the system, it will usually be a smaller part of a bigger system. Not always, but most examples, you'll see that. All right? So we'll have multiple of these delta S terms, which of course is implied below. Okay? Now, as far as the temperature of the system, as I said, it actually only works as written in this formula if the temperature is constant. The temperature must be constant for the formula to be used exactly. Okay, there is a calculus approach to using, finding the exact values when the temperature is changing, but we here are just covering an algebraic approach. The temperature, however, with this algebraic approach, can be estimated, right? So the temperature can be averaged, right, during a process that changes the entropy, and that will give a good estimation for change in entropy, okay? All right, so we'd plug in T average, so this would be T equaling T average as an approximation technique, and I'll show you an example of that. Now, finally, the change in entropy of a system compared to the environment must always be greater than zero. All right, just a restatement of the second law of thermodynamics, okay, in equation form. Change in entropy of a closed system and its surroundings, okay? Now, notice that it's a closed system, not an isolated system. That's a system that can exchange energy, like the Earth, but isn't exchanging significant amount of mass with the universe around it, right? Earth is basically a constant in mass, except for, mass getting added to Earth. But there is a significant amount of energy coming into Earth and being released from it. But the idea then is if Earth was a system here, the change in energy of the system plus the change in energy of the environment, which is the surrounding universe, must be greater than or equal to zero. Now the thing is, when could it be equal? Only theoretically. In reality, it's impossible for it to be equal, all right? But if the total change in entropy is, or the case where it's only equal to zero, is if the thermal processes were done infinitely slowly, okay? So in other words, you'd have to be able to do reversible processes, which is impossible. Another way of thinking about it is there's one example that ties in with material we've seen before, is that if you ran a Carnot engine, the Carnot engine should have a total change in entropy of inside the engine plus the outside world, like the exhaust from the engine and so on, and how much work the engine does. That total change would be exactly equal to zero for a Carnot engine if you're running it at 100% efficiency. But that would take, of course, running the Carnot engine at absolute zero, which requires an infinite amount of energy to get there. So something that's theoretical, but the theory tells you that it's also impossible because it takes an infinite amount, or it has to be done infinitely slowly. So you see that there's two ways of saying that it's theoretically possible, but also unachievable. Now let's take a look at our examples. Okay, so we have different types of practice problems as well as a concept question you'll see. So we have type 1, simple problems that involve a change in entropy of a system where there is only a phase change. Why only a phase change? Because that makes it so we can use the equation exactly, the one we just saw, because the temperature is constant, but there is a change in Q, all right, or there is a value of Q. Heat, that is. Type 2, problems that involve an estimated change in entropy because the temperature did change, okay? More practical, more types of examples we can do there. We're pretty hemmed in with type 1, but unfortunately an estimate. And finally, type 3, problems that involve changes in entropy related to heat engines. So as I've said a couple times in the introduction, back to taking it to heat cycles, efficiency, Carnot engines even, seeing that. So let's take a look at our first simple example, example 1. 1 cubic centimeter of water at a temperature of 100 degrees Celsius is boiled into water vapor at that same temperature. So no temperature change, just the phase change. What is the change in entropy of the water as it goes from liquid to vapor? And the heat of vaporization is 2.256 million joules per kilogram. Okay, so here's the formula. Notice that we are just going to use our value of Q here, the value to boil this much water, which is a cubic centimeter. And our temperature is just going to be 100. All right, but converted, importantly, to Kelvin. All right, so 373 for the temperature. Here is the amount, the mass of 1 cubic centimeter based on the density of water, right, which I assume we know here. And there's that latent heat of fusion. Works all out, so that's our, those two terms together, the product. That, of course, is the Q, the heat to boil. And there's our change in entropy, 6.05 joules per Kelvin. Okay, a lot of times we're going to see thousands of joules per Kelvin when we look at entropy changes, but of course this was a very small system. It was just 1 cubic centimeter, tiny amount of water, like a spoonful. But there it is, a way to exactly calculate entropy for a system where there's only a phase change. Okay, what about example 2? In this case, a sink full of water at 20 degrees Celsius and a volume of 0.3 cubic meters has 1 liter of hotter water, 95 degree water, poured into it. What is the total change in entropy of the mixture? So first we have to do a little mini calorimetry problem here because this is an isolated system that's going to approach equilibrium. So the 20 degree water and the 95 degree water will approach some equilibrium. All right. Now notice that it's a sink and it's a small amount of water. So that means that we actually don't know the volume of the sink. We're just going to assume it's very large. That's going to make it even easier to calculate the final temperature. And let's then from there, we're going to look at how to calculate the change in entropy with 2 entropy change terms. So an entropy change term for the big sink and a second entropy change term for the water that was poured in, the hot water. So what does it look like? Okay, so the change in entropy of the overall composite system is the cold water that was there, the sink water, and the poured in hot water, the change of each. And we need T final, which we get from calorimetry. So we set up a closed system calorimetry with the mass of the water, the initial water, the specific heat of the water, the change in temperature, the mass of the hot water that's poured in, the specific heat of water again, and then the change in temperature of the hot water. Okay, we'll go ahead and rewrite this. So we have here that the sink, all right, oh, that's right, wait, I misspoke. the sink does have a known volume. So we're not just so in this case, we're doing a fuller but still simple calorimetry problem, just mixing hot and cold water, no phase changes. We have 300 kilograms of water initially because it's 0.3 cubic meters. It's a large sink. All right. And there's that T final of both the hot and cold water. The 1 liter, that's 1 kilogram. So in both cases, we converted the volume to a mass based on the density of water, all right, which is 1,000 kilograms per cubic meter. There's the specific heat of water showing up both times. And there's the T final that's going to be shared by both of them, and they're two different initial temperatures. Okay? So when we go ahead and solve for that, in which we've would have seen fully in other lectures, so here we'll skip over that extra work, we find that T final is 20.25, which makes sense because the large sink is going to by far dominate where the equilibrium is going to show up compared to just the 1 liter of water it's poured in. Okay, in other words, the 1 liter of water just heats it up marginally. But that's not enough because since we're going to use entropy, T final is almost the last step in considering our temperatures. We have to find the average temperature for both of the systems being the cold water and the poured in hot water, because that way we can calculate the change in entropy for both. Okay, but they have different average temperatures. They both reach the same equilibrium temperature, but their averages are different. Okay, so the average temperature of the cold water would be its initial temperature, 20 degrees Celsius, plus the final equilibrium temperature divided by 2. Well, the equilibrium temperature is just a little bit hotter than how it started, so its average is 20.13, even closer to its initial. But for the hot water, well, there's going to be a average that's way off from the equilibrium, right? Because it started at 95, its final temperature was 20.25, so that means its average temperature was 57.63 degrees Celsius. So now we can estimate the change in entropy, because this is the method where we use those averages and we're estimating, okay? So in both cases, we have our Q on top, all right? One of them is going to be positive, one of them is going to be negative, which will just come up naturally from the change in temperature, all right? And then we'll put in our relevant masses, just like we did when we actually found that equilibrium temperature. So we're plugging in a lot of the information again that we used when we did the calorimetry, because now we're calculating entropy. Notice that in the denominator, it's the average temperature, which are different values for the two systems respectively, and they're importantly converted to Kelvin. Got to convert them over. Okay, so then we see that there's one of the parts of the system gains entropy, the other part loses it. Okay, because that's the thing. There is a an overall pull and take and pull, but notice which one's bigger. Okay, so the cold water that heated up just marginally, but there was so much of it, the cold water gained entropy. It became more disordered. Okay. Meanwhile, the hot water, which was in this, disordered state, near boiling, right? It actually became more orderly and it lost entropy. But notice that the amount that was lost by the hot water is smaller than the amount that was gained by the cold water. And that's always the case. Okay? Even with this imperfect method of taking averages, you'll still always see confirmation of the second law of thermodynamics that entropy increases. Okay? In any process like this. So the total change entropy of the total system with its two parts is 121 joules per Kelvin. Okay? An increase in entropy. Now let's go on to our concept question. Question 1. Some incorrectly say that the second law of thermodynamics contradicts the theory of evolution. Because if entropy is always increasing, how could you, naturally get something that's so orderly like life? Look how orderly life is, from trees to the cells of animals, right? Very ordered, amazing system. That couldn't just have happened naturally. That contradicts entropy. Okay, well, let's see. Okay, well, the Earth absorbs about 3.5 times 10 to the 24 joules, right? So a huge amount of energy, and that's radiative heat energy from the sun every year. So that's how much energy comes into the Earth every year from the sun. The average temperature of the surface of the Earth is 280 Kelvin, okay? And the sun's surface temperature is 6,000 Kelvin, okay? Which is a medium for stars. We can generously assume that the biomass on Earth is 10 to the 16 kilograms. Everything from plants to microscopic animals to humans, everything together, 10 to the 16 kilograms. And the energy required to turn disorganized matter, so just a bunch of random molecules, into the orderly arrays of cells, all right, into organized life, is equivalent to cooling 10,000 degree or 10,000 Kelvin water, so very, very hot water, superheated steam, to absolute zero water. Okay, so this is just a rough estimate to say, okay, well, this is a huge amount of energy. Okay, well, and that would be for every bit of mass. Well, that's what it would take to build up from random gas, random molecules to ordered life. So given these numbers, does 3.5 billion years of evolution seem impossible given the energy input of the sun? Because the idea is if the second law of thermodynamics really contradicts evolution, that's a big deal, right? But it doesn't at all. Because saying that, yes, systems become more disordered doesn't mean that you can't have pockets of ordered. It's possible to create pockets of more orderly systems, especially if there's enough energy to do so. And there's plenty of energy, as we'll show, coming from the sun to explain ordering molecules into the life we see on the surface of the planet. So the total energy required for evolution on Earth is as follows. So the energy to evolve would be the biomass plus the specific energy of, or the specific heat of steam, the change in temperature of the steam, which is going to be 10,000 Kelvin all the way down to 373 Kelvin, right, which is 100 degrees Celsius, plus the actual energy to then condense all that steam, because the idea is we need to find out how much energy it takes to go from 10,000 Kelvin to 0 Kelvin, absolute zero. Then we got the whole cooling of the liquid phase of the water, again with a huge biomass, the generous estimate here, okay? Then the freezing of it, and then finally the cooling of the ice all the way down to zero, okay? So when we plug in all those numbers with that huge leading mass, we end up with 2.29 times 10 to the 23 joules, okay? So how does that compare to how much energy we're getting? Well, wait, we were getting that much energy every year. Wow. So the heat value given for absorbed solar energy is actually Q net and already accounts for the energy reflected and emitted back into space. So that means that the temperature of the sun and the earth are not even needed. So we see that there is enough energy in a single year, let alone 3.5 billion of them, coming from the sun to explain evolution. But of course, not all the input energy goes to evolution. Therefore, there are no valid energy arguments to be made against evolution, not even close. Not even, it's with our generous estimates, we still have enough energy every year. Okay. Now, again, and the point being here that, yeah, a lot of energy goes to driving the weather and currents in the ocean and all the other processes we see on the surface of the planet. But there's still enough energy to go around. Okay. Plenty. Right? If you had a very, very cold planet very far away from a star, then it becomes a better question, right? There might not be enough energy on that very cold, distant planet like Pluto to actually explain, evolution happening. But not so on a warm planet like ours. Okay? We just have the right conditions. Example 3. This is the last one. This is going to be the one that involves a heat engine, as was mentioned in the different types of problems. So a real heat engine working between heat reservoirs of 970 Kelvin and 650 Kelvin, so no need to convert since they're already given in Kelvin, produces 550 joules of work per cycle for a heat input of 2,500 joules. Now do note that since we were told both the temperatures of the hot and cold reservoirs as well as the heat flow from the hot and cold reservoirs, that means we're definitely going to be comparing between actual efficiency and ideal efficiency. Whenever you're given both sets of numbers, that means there's going to be some comparison. And indeed, if you look at part A, it says compare the efficiency of this real heat engine to that of an ideal Carnot engine. And that would be one that's entirely based on temperature with the Carnot cycle. And that one is where we'd use the temperature values of the reservoirs. Okay, so let's do the real energy or real efficiency first, the actual efficiency. That's just the work that the engine does divided by how much heat input it gets. Okay, well, we're told that it does 550 joules of work, and we're also told that it receives 2,500 joules, right, of the Q flowing in. So we got the values to calculate it right away. No need to even use the first law of thermodynamics. And we end up with an efficiency of 0.22 or 22%. All right, well, the ideal efficiency based on the temperatures that were reported comes out to be, plugging in the values in kelvins, or in Kelvin, 0.33, okay? So indeed, if we take the ratio of the actual efficiency to the ideal efficiency, we find that it's operating at about 0.67 of ideal, okay? All right, good for those particular temperatures. Now, something new. Calculate the total entropy change of the universe per cycle of the real engine and compare that to if the engine was in fact ideal operating between these temperatures. Okay? Well, here it is for the real case. Here we're just going to look at the two flows of entropy, right? One is going to have QH, that is going to be the entropy or the heat coming in and the temperature of the hot reservoir. One is going to be the exhaust and the temperature of the cold reservoir. And we'll note here that this makes sense to take this step here because as a hot reservoir gives up heat, it loses entropy. That's why this one's negative, right? The hot reservoir cooling it's becoming more orderly. Anytime something cools, it's becoming more ordered, and it is having a decrease in entropy always at the cost, as we know, of something around it having an increase in entropy that's larger than its decrease. Okay, so, and that's of course as the cold reservoir receives heat, it gains entropy, which is why this term is positive. All right, so from conservation of energy, in other words, the first law of thermodynamics, we know that there's a relationship between the work done and the heat coming from the hot reservoir, which allows us to numerically solve for QL, or just do a substitution. So we're just going to substitute this value into here. And then we'll look at the total change in entropy with that substitution, and now being able to plug in all known values. And we'll go ahead and do so with the 2500 of the heat coming in, making sure to remember that term is negative and the hot reservoir is operating at 970 Kelvin. And then looking at the exhaust, which is 1950 joules, that's the QL, and that is into the cold reservoir operating at 650 with a gain in entropy. All right, this term ends up being larger than this one. All right, so that means, of course, that the net change is positive, and it's 0.42 joules per Kelvin. Okay, so not a lot per cycle, but I mean, maybe this engine is running at 500 hertz, so 500 cycles per second. Well, then it would add up. All right, so what if the engine is ideal? Okay, well, in that case, we would replace the work with the ideal times QH. Okay, so the work it would do would be 825 joules. Okay, so it would be doing more work. Why do we have to do this step here? Well, because the only information we're given about the ideal engine is the temperatures. So we're just taking an ideal engine that operates between those temperatures, but that would be doing a different amount of work. It'd be a different engine than the real one that was reported here. And it'd be doing significantly more work at 825 instead of 550. Okay? And this is just using this formula here, but replacing E with E ideal. So you can see. Okay? So then we'll go ahead and use the first law of thermodynamics to find QL numerically, and it would be 1675. That would be the exhaust. So the exhaust is actually less than in the less efficient case. So it's doing more work with less exhaust. Well, indeed, it's more efficient. All right, so then we'll go ahead and find the change in entropy of the system with our two terms, and look what we get, exactly 0. So actually, I misspoke a while ago because I said that a Carnot engine, only if it's ran at absolute 0, will have a net change of 0 entropy. That's actually not the case. Carnot engines always have a net change of 0 entropy. They are truly an ideal engine. But what really makes that impossible was the point on the first page where I said it had to be run impossibly slow. And it's the basically, if you think of the Carnot cycle, which has 2 adiabatics and 2 isotherms, it is the timing that makes it impossible to ever achieve a perfect Carnot engine, because the adiabatics have to be infinitely fast in their expansion and contraction, and the isotherms have to be infinitely slow to actually be a perfect isotherm. And only then would you have a perfect Carnot cycle, an impossible task, and it would indeed have a net change of 0 entropy between it and the outside world. But can never happen, but interesting theory to think about. Okay, well, hopefully these numbers confirm a lot of what we can do with entropy, a way to quantify disorder, and a way to numerically understand the second law of thermodynamics. Thank you so much for watching.